first time I'm giving a project presentation, so I have no idea what I'm doing. So imagine that you want to measure the distance to a galaxy. You can't just like shoot some laser to the galaxy and wait it to bounce back and time the time it travels with the speed of light, because even the nearest galaxy to us is like 2.5 million light years away from us. So it takes like 5 million years for light to travel back. By the time it travels back, perhaps Chinese people have already colonized the Milky Way. So you also can like just measure the angle to the galaxy and try to figure out the parsec, because the galaxy is too far away that the angle here is almost 0 and the angle here is like 90 degrees. So it will be very inaccurate. So what I'm trying to do here is to try to use some formulas to derive another way to have the distance to another galaxy. And this picture is taken from Skynet. This is NGC 496946, which is the galaxy I'm studying. Right. Can we go to the next one? All right. So if we're trying to use some formulas to derive the distance, we better have a formula that's with the distance. So if we look at Kepler's third law, so the first equation here is like directly Kepler's third law. If we divide 1r here and get this one, so we can see this as 2 pi r divided by p squared. So 2 pi r is the circumsphere of the galaxy and p is the period. So if we use the time to divide a circumsphere, we'll have the velocity. So we can have this one. And this will be the distance to our target galaxy. And then we have another expression. This is the inverse square law of our luminosity. And if we use the first one divided, oops. So if we divide our first expression by the second one, we'll get the expression here. So we have our distance to our galaxy. So the rest of things we're going to do is to find the value of the angular radius of the galaxy, the rotation velocity of the galaxy, the flux of the galaxy, the mass of the galaxy, and the luminosity of the galaxy. Sounds quite simple. So in order to make it a little bit easier, I'm trying to introduce this one as a new quantity called mass to light ratio. So this one is generally the quotient of the mass of a spatial volume, especially of a galaxy or cluster, and its total luminosity. So if I describe it in English, it means for a star to generate unit luminosity, how much mass is required. Right. Can we go to the next one? So these two are the assumptions that I'm going to use in order to facilitate our calculation. The first one is that the mass to light ratio, we talked about that m/L. We assume that our target galaxy's m/L is kind of the same of the Milky Way's, because you can imagine that for all the stars, they kind of use the same mass to generate same amount of luminosity. And the second assumption is our target galaxy's disk is circular. I only make the second assumption to facilitate the calculation, but also because although it's elliptical, the major semi-axis is quite close to the minor semi-axis. It goes to the next one. So next we're going to find out the quantities of the galaxy we derive except for the d, so that we can calculate the d. So the first one is the mass to light ratio, and I'm going to find out the m/L by using one of our labs is this nearby star catalog. So if we add up all the luminosity, we'll get a value. And if we add up all the mass of the stars that in our within 50 parsec, we can have the mass. So if we divide their mass by their total luminosity, we can have the m over L. That's, I think, is here in the equation. So we can have, yeah, that's the first part we're going to calculate in the next slide. And the second one is the tangent theta, is the angular radius of the galaxy. Yeah. So since we have assumed that the galaxy is a circle, I just simply make an average of the major diameter and the minor diameter and divide the value by 2 to have the angular radius. Next. Yeah, and this plot is called the rotation curve. So for a disk galaxy, the rotation curve is a plot with their orbital velocity against the distance to the center of the galaxy. So imagine if this is the center of the galaxy and the galaxy is rotating this way, of course the center doesn't move, so the velocity of the center is 0. And as you go out of the galaxy, it rotates faster and faster for the orbital velocity. So these 3 lines are 3 different datas. I just simply took the average, so it's approximately 180 kilometers per second. Next. So I found the magnitude, the apparent visual magnitude of NGC 6946 online. And I also know the solar magnitude of the sun and the solar flux of the sun. These two we're quite familiar with, and we can use this expression to find the flux of our galaxy, since this one is the only unknown quantity. We have already known the flux of the sun and the magnitude of both systems. Right, next. And then if we put the d here to the front, we can have an expression of the distance to our target galaxy. And the angular radius, rotation velocity, and the flux, this is the flux of the galaxy, presented by the equation from the previous slide. And we have the L over m through the nearby star catalog, and the gravitational constant is a constant, and 4pi is also constant. So that way we can have the distance to another galaxy.
What's the end?
Can we refresh?
I don't see a refresh button.
Control R.
Or
No, it's Windows, it's F5. That works too.
what do I do? Sorry.
F5 works as well.
I can
Nice.
Can you click here?
here.
Yeah.
Mm-hmm.
I think you just
Is
download
it
It
in
just
the-
opened it.
Oh,
yeah.
they downloaded it, so now it should
Click
be able
here.
to load
Yeah,
better.
is it, maybe it opened a new window and it's over there.
This is
You
it.
just
Open?
open it.
Oh.
Where are we? Ah.
And then just open
Yeah, open
this
it.
one. Yeah. You don't want to confirm my calculation because it takes my 5 times to put numbers right on the calculator.
And the units, right?
And the units, right?
Yeah. What is
You
that?
can go to the next page.
We'll have to do it.
So this is a graph I took from a website from NASA of the different results of the distance of the galaxy measured by different astronomers. So if we look here, this is the minimum value, this is the maximum value.
Wow.
So even the professional folks of NASA disagree with each other on the result. So I think it once again confirmed my theory that science isn't some easy way out. That we don't do it because it's easy. We do it because it's hard. And to measure the distance to another galaxy is hard. And it's very important. Say, if humans are trying to colonize another galaxy and we don't know the exact distance to the other galaxy, and we just kind of open a portal and teleport our ships there. And chances are our ship ended up into the center of a star and make us popcorns. But it's always good to try all the possibilities to see if we can find another path to our answer. So I think what I've done here is to try to find an indirect path to what's kind of difficult to have. Right, I think that's all. Thank you.
What was the result that you found for your distance away?
It was 42 megaparsec, which is kind of 3 times bigger than the folks have in NASA. Okay. Yes.
According to your personal estimation, how accurate do you think your result is?
All right. So I think the assumption, I made 2 assumptions, right? So I think the second assumption doesn't make a big change. I think the major error of this project is the first assumption, the mass over L. I assume that this is our galaxy's M over L is the same with theirs. But since I have no idea what's going on there, so probably this have a major difference. Actually, when I first finished my calculation, the result is like 30 times bigger than the results. And I go back, so the star catalog we used is within 25 parsec. So I try to make the radius larger. So I tried the 50 parsec, and the result made more sense.
Was there anything about the galaxy you looked at that made it especially attractive to do these calculations, or was it just like a random
No, I
thing?
just choose the galaxy because it looks good. and it has a clear picture from the sky now, because I don't have more credits. Yes.
According to what I know, we usually measure the distances to galaxies using redshift, Doppler effect.
Yeah. The
So,
professor yesterday also talked about Doppler shift.
so can you explain a little bit does your method have an advantage over it? Because I think it takes more effort, right? So can it be more accurate, or is there other advantages?
So if you're I think if you're measuring the Doppler shift of the galaxy, the galaxy is moving quite slowly. So only 2,000 kilometers per second, but the distance is rather very distant. So perhaps it's very hard to measure the Doppler shift because it moves so slowly that it doesn't make quite a big difference.
What is the biggest uncertainty in your calculation, and how do you think you can improve it?
Well, I think the biggest uncertainty is the mass to light ratio. I think one way to improve it is to just try to find the exact mass to ratio of that galaxy. But I think it's rather hard because it's probably difficult to determine the luminosity and the total mass of that galaxy. Yes.
Can you explain why the mass luminosity ratio differs so obvious so implicitly into galaxies? I mean, they should be the same.
So I think it depends on different stars you have. So say if you have a tiny star and you have a giant star, as we learned, different stars use different fuel. So the unit mass they generate the certain amount of luminosity. For example, in the core of, for example, this is iron, and that for our sun it's hydrogen. I think it should be different.
I just have a little question for your the meaning of this project. I mean, your motivation is good and it's very meaningful in some extent, but just I have a question that is, since the light you are observing from the galaxy is like emitted billions years ago, and so it travels billions of years to come to Earth, so you can observe its location is there, and the distance you measure is like the distance between us and its location billions of years ago, and it's not the distance between its current location and here. So do you find it still meaningful to do such distance, or you are trying to improve your calculation to get more approach the reality?
Yeah, I see what you're saying here. So you're saying like the light traveled billions of years and perhaps the galaxy has already moved away, right?
Yeah, you
So,
cannot
yeah,
project
yeah.
its future motion.
Yeah, I agree. So first, I want to do this project because it is very interesting. Yeah, it sounds fun. And second, since first my measurement itself is not quite accurate, and plus the distance is so far away that even it's moving, so I think it's not a major problem.
So you know how each value used in your calculation will have like a certain uncertainty, like a plus minus a certain value? If you propagate those uncertainties, you would be able to find uncertainty to your calculation. So what would you estimate this value to be?
I have no idea.
Um,
I see your point. So like try to estimate the maximum and minimum value of my quantities, right?
yeah.
I think that's one way to improve my project. I think is time.
Yeah. Yeah.
Thank you. Thank you very much.
So should I go?
So is your
Yeah.
Bye.